So we start again. So I updated my very modern web page, and if you see that it was created in the 50th anniversary of the creation of CERN, and we actually celebrated the 70th anniversary in November at CERN. So that now is a vintage web page. So I keep it. So I updated, I added the notes of yesterday, and you can find the notes of today. And there is also a write-up that I compiled a few years ago, which you can use to check whether the formulas I write on the blackboard are correct or vice versa. Okay, so today we have is a loop day. I saw that Ian calculated the loop, one loop. How many loops? One? Yeah, okay. And I also dare, and we will also dare together to compute a loop on the blackboard, because it will be useful, and hopefully we'll learn a lot of things from just one loop computations. So that's the hope. So we start with writing down the collider master formula number 2. So again, imagine that you collide, in this case, two protons, or in general, any collision actually, PE, PE, for example. And then you produce a final state, which is composed by many particles going out. So this is exactly the setup of a scattering experiment, right? The collider, but also the scattering theory in quantum field theory. And it was mentioned yesterday, all the tools that we basically developed during our courses at the master level were designed to go from a Lagrangian, right, to a scattering amplitude. Let me call it IM. So I assume that you more or less know how works. How do we manage to go from a Lagrangian to a scattering amplitude? Okay, so now I have a question for you. Which of these two objects is more fundamental? I mean, it is where really the physics is. On the left, where we write on the t-shirts, or on the right, which we never write anywhere. Which one? Left? Right? Right, okay. Very good. So remember that Lagrangian is not really a physical object per se, and it was explained yesterday very well by Ian. I mean, you can do filter definitions, right? You can change the way a Lagrangian looks. You can change even the kind of degrees of freedom that might appear at once. You can always redefine things in a way that at the end, the scattering amplitudes, which are related at the end to observables, are the physical objects. Of course, we have to square them. Overall, there is a global phase, which we are not sensitive to, but somewhat the relation really with the observable is done through the scattering amplitudes. So the scattering amplitudes are the fundamental objects of our technology that bring us to be able to calculate these amplitudes. And in my course, at least, I only think about interaction which are perturbative. So when I give results or I say things, I always mean something like QCD in the perturbative regime or electroweak interactions, or anyway QED alone, something that I can compute perturbatively. So how I compute a probability for a given observable? So let me indicate with sigma. Sigma is a cross-section in general, right, which is the key observable that we relate at colliders. But more in general, right, we want the cross-section, so what the probability for some observable to be measured at colliders. So we write this in a form that you must be familiar with. So let me write it and then we comment. So there is a flux, right? This is a normalization of the initial state, right? Of course, the rate depends how many particles we feed in the flux at the beginning, and therefore we always have to normalize our probability in a correct way. If you derive the formula of a cross-section, you see that here, hidden here, is that there are a lot of normalizations. The normalization of initial particle, the normalization of the free fields, and so on. At the end of the day, it all amounts to this term here. And then there is a sum over final states, because we have a plethora of final states that we can produce, and different final states might contribute to the same observable. So this is a key point that we use in perturbation theory, always, basically, to be sure somewhat that what we are going to calculate can be actually observed. Okay, so this is a condition from the theory point of view, but also a condition that has to be matched also at the experimental level to be sure that we are doing the same thing and we can compare theory with data. And then, so this is a sum over final state. And then for each one of the final state, there is a phase space integral. So you sum over all possible directions where your final state composed maybe, for example, by n particle. Each particle can go anywhere, right? So you have a phase space that has to be folded in, on which you integrate. Then you have our matrix element squared, which is what we calculate. So again, the physics, my predictions, right, my model is here. Okay, the rest is kinematics, so to speak. And then we have a function which depends on the final state position. So that this weighting function depends on the point in phase space that we normally so if we write a cross section, we don't think about it, and in our mind we set this to 1. In fact, we are already using it. Okay, so in general, we should always think that we have some kind of function here which selects the final state. So this formula is full inclusive in the way, so I'm summing over all possible final state, and then I'm doing the selection, like I want to calculate the cross-section for the Higgs boson. Then I say, well, I want my observable, if I have a Higgs in the final state, will be 1. If I don't have any Higgs, will be 0. So it's like a binary function. And I select everything in the final, all possible final state that have 1 Higgs. Okay? Is that clear? More technically, if you then go to more sophisticated observable like jets, then this is really necessary, actually, even in a non-trivial way, to come, or you go higher orders, as we will see, in general. This function, this weight, this selection allows us to put together final state which, for our experimental observable, are degenerate. Okay? So that they will all end up in the measurement. And we always have to do that, to add all final state that somewhat contribute to my definition of a final state. Otherwise, we risk this prediction not to be, we say technically infrared safe, but more in general, really what it means, it cannot be compared with my experimental observable in a reliable way. Okay, that's what it really means. That there are configurations in phase space which are the same, and then we have to sum them. So one example that you can keep in your mind is the fact that imagine that in your experiment, a photon is radiated with a given energy. If this energy is below the threshold of any of the detectors that you have in your experiment, then if that photon is there or not, you cannot tell. And therefore, you have to sum both the final state with no photon and with the photon up to the energy of the threshold of your experiment. Okay, so that's a very simple example to keep in mind. Okay, so inclusiveness, despite latest development in the US, is one of the key ingredients of physics, right? We cannot get rid one day saying, well, we are not inclusive anymore, right? All our predictions will just be thrown out of the window. So inclusiveness is a must in all predictions that we are able to compute. And the other thing that I want to stress now is that you should have a feeling also of how difficult it is to compute this, just for you to give an idea, right? So even at tree level, this is complicated from some point on. So we are used to do computation our own in school, and these are like 2 to 1 or 2 to 2. We will do a 2 to 1 today on the blackboard. But I mean, I think you have your own experience in knowing, right, that computing matrix element is complicated because the number of Feynman diagram grows actually exponentially, factorially. When the particles are identical, it even grows factorially. So it's a huge number, and you know that something that grows factorially, at some point there is a wall, whatever computer you have, right? At some point you will be stuck. So this computation can be difficult. Over many years, many techniques have been developed to simplify it. So now it's manageable to compute this at tree level and even in one loop for basically any process we are interested in, okay, in colliders. The other thing which is difficult is this integration over phase space. Because what is the dimension of a phase space? Okay, so the phase space is each particle has 4 degrees of freedom. 1 goes away because of the mass shell condition. It remains 3, right? But then there is an overall conservation of momentum, which is -4. So it's 3n minus 4, the dimension of a phase space. So you have to count the number of particles, like, 10 particles, 30 minus 4, 26 dimension. Okay, so if you ever try to do an integral in more than 3 or 4 dimensions, you realize that's not an easy thing to do. So there is a lot of techniques that we use nowadays to do this computation, 3 level and 1 loop, but it's not, in general, an easy job. Now, this is a simplified formula where you see, actually you don't see because I didn't write it here, but I mentioned generically A and B as my initial state. So I didn't go into the details of what I have to do, for example, with protons, where I have actually scattering partons. Okay, so let me prepare the ground. Let me be a bit quick here because I'm pretty sure that you know this well. So if you have a proton-proton collision, right? What we say is that there will be a parton 1 in proton 1, which will have the energy of a fraction of the energy of the beam 1, and x2 with a fraction of the energy of beam 2. If you are in the center of mass frame of the collision, then you can use the same energy. So this is the beam energy, okay? So for in the collision of the proton, and this is, if you want, the momentum, right? So if you write this in terms of momentum, you will say that this is like this, and P2 is 1, and this is x2 P2. Okay, so the fraction of the momentum of the encoding proton. At very high energy, I neglect, right? When I'm at collider, I can neglect the mass of the proton. That's not a problem because we are at very high energy. Then we define, we will be using later, a quantity tau, which is defined as x1, x2, so that the energy in the parton rest frame is so S, capital S, is P1 B1 plus P2, right, square. I'm sure you have seen this. So the energy available in the center of mass is lower than the total energy because x1 and x2 are numbers, are quantities which are less than 1. And then we define tau, right, then is S hat over S. And then we also define another quantity, which is called rapidity. I will define two kinds of rapidity. So let me call it rapidity of the center of mass. And this is y, which is 1/2 log of x1 over x2. So what is the rapidity? It's basically the boost in the z direction of the center of mass point. Okay? So if x1, x2 are not the same, then the center of mass is boosted in one direction or the other, right? Because one energy is larger. If they are the same, there is no boost. The center of mass of the particles is the same as the lab, and then the rapidity is 0. Okay, so if x1 is equal to x2, the rapidity of the center of mass is 0. Okay, so that's the first rapidity that we use today. And then to close on the kinematics, again, it's very convenient to use the center of mass frame of the two particles, P1, so let me call it x1 P1 and x1 P1. Okay, so here I can go to the rest frame. Okay, I can go to the rest frame for the particles. So in this case, the variable that I have are S hat and theta, which is the scattering angle if there are two particles, or if there are more, each one will have its own theta. And of course, if you are then in the lab, okay, in the lab, the same event, right? Imagine that is boosted in this direction will look like this. Okay, for example. So in the lab, an event which is back-to-back in the center of mass frame is not back-to-back, right? Obviously. And therefore, I will have to make a transformation, a Lorentz boost in this direction to go from here to here. So the way we do this is using a Lorentz transformation, which I remind you can be written in this way. So the transverse components do not change. So the P perp star is equal to P perp in the lab, right? If you boost this way, the components which are transverse don't change under the boost. So these are invariant, the 2, 1, x and y, let's say. And then on the z direction, I have the usual Lorentz transformation, which mixes E with P. And then, of course, we know that gamma is gamma squared minus gamma squared beta squared is 1. And then we can rewrite this transformation as a pseudo rotation, right? Hyperbolic rotation of a given angle. And this is the transformation that we use to go from the lab to the center of mass and vice versa. So now I define a quantity. So there is the textbook way and a bit more advanced way, but using light coordinates. It doesn't matter, it's the same thing. So you can define P plus P minus equal E plus minus PZ if you want. And then you define, you look at the transformation property of E plus P over E minus PZ. This is P plus over P minus, okay? And then you check how these P plus and P minus transform are Lorentz boosts, okay? You can do it from here. This will be, so this is the prime now, or the star. So this will be E plus PZ, let me erase this here. So E plus, let me go here, voila, and I get E plus PZ, E minus PZ, and then you see that here you get a cosinus plus sinus, here you get a cosinus minus sinus, and then you multiply both up and down by cos plus, and then cosinus squared minus sinus squared is actually 1. Okay, so this one is 1. And then what you see is that this ratio, you can also do it using this transformation, p plus p minus prime equal e omega e to the minus omega p plus p minus, which is more elegant. So this is a rotation of 45 degrees. So I'm defining these two variables. And then you see that this rotation is actually two different independent boosts, one in the forward light cone and the another one backwards in the light cone. And you see that the resulting quantity is just a number which is dependent on the booster, but it doesn't mix this quantity again. So the result of this is that the booster, if I define a quantity which I call rapidity, 1/2 log of E plus E minus Pz, this quantity under a Lorentz booster changes by a constant, because the log stays the same and then is multiplied by a number, and this number I put plus a number. Okay, so this it scales, it changes uniformly with the translation. So under Lorentz booster, the rapidity changes by a constant that depends only on the booster. So it's not invariant, but now you have a measure, because if you have two particles in your final state or more particles, now you can define a distance between them, which is Lorentz invariant. Okay, so now you say that you have particle 1 with rapidity 1 minus particle 2 with rapidity 2. This object is Lorentz invariant because the constant will cancel between y1 and y2. So this is invariant. Therefore, I can build a distance now, which is delta y squared plus delta phi, for example, squared, right? So delta phi is the angle between the two particles in the transverse plane. And then in the plane, so you have to think about a cylinder. Okay, and so this is a measure which is Lorentz invariant under boost in this direction on a collider symmetric system, which is a cylinder. Okay, so this distance is Lorentz invariant under boost in this direction. And that's the reason why we use the colliders, because in principle we never know, right? I mean, you might not know, depends on the final state, you might not know what is the Platonic center of mass. So we want quantities which are invariant. So the distance between two particles is invariant. The other things which are invariant are the projection of the momentum, right, of the momentum of the particle along the transverse direction. Okay, so here you have x, y, and z. Okay, and the projection of x and y on the momentum. Okay, this projection, so this projection and then this projection here, this one and this one, these are invariant under boost because it's transverse. So in colliders, we always use transverse PP collider, we always use transverse quantities because they are frame independent, Lorentz frame independent on this direction, and they're not, and they are invariant, right? And we can measure them. Okay, so typically the quantities which we are interested in will be transverse quantities. Okay, like for example, the PT of a particle, right? The transverse energy of a particle. And then we can also, right? We can also build, as we said yesterday, invariant masses, right? If we measure the all the momentum, the energy, and the direction of a particle, I also can build quantities like the invariant masses, which are Lorentz invariant to court. Okay. Okay. So this is the introduction. Are there questions? Is there anything? Is it everything clear? So whenever we can see a particle, because it's charged, it leaves a track in the detector, and then energy in the calorimeter, we can build the form momentum and build even invariant masses. For example, a photon, so you say a photon is neutral, so it doesn't leave any track in your detector, in your tracker, but it leaves a signal in your calorimeter. So if your calorimeter is very well segmented, you know also the angle, you know where it comes from the rest of the events. So you can track it down to the interaction point. Then you know the four components, then the three components of a photon, and then you can build a true mass invariant. Okay, the same with with other particles. But it works also for photons. That's what I wanted to say. Okay, good. So this is a useful information for later. So now we instead take a small advancement, right? We add a bit of information and we specialize our master formula generic here to the PP collision. Okay, so this one was general, and now we go to the PP collision, and we rewrite. Now I leave out the information on the measurement because I'm really talking about now with the caveat which I told you before about a cross section. So the probability of producing a Higgs boson, and that's what we will calculate today. Okay, so the probability for producing a Higgs boson. So first question, of course, will be a Higgs boson inclusive. So in fact, let me write here plus x, okay? Which means I only require that at least I see a Higgs boson in my final state. At the end, as we said yesterday, I don't even see a Higgs boson, right? I see the decay products. But let's simplify for the moment, okay? There is a good reason to do that. So this is 2 over the energy of S. Now, the energy of the collider over sum over ij, sum over x, the integral of d phi n x, so e plus nx, let me put it, dx1, dx2, f I x1 mu f, I'll explain what it is, j x2 mu f times sigma ij to x plus x. Actually, to be really precise, this object also will depend on mu f and in general on renormalization scale. And this x, which is here, is not the same x which is here. So let me call it x prime. Okay? So it looks like I'm pedantic, but I'm actually, it's important for us to understand really what this thing means. Okay? So I think that you have seen this already many times because it's in all textbook and so on. So what I would like to tell you really before doing a computation is actually what it really means. What is the meaning of this formula behind the scenes? There is a lot of information that is codified, that we take for granted in this formula, which actually is non-trivial at all. So the first one, you see that we have written our cross-section as an incoherent sum over the partons. So this, I call it a short distance cross-section, is the partonic cross-section. And I and J can be quarks, anti-quarks, or gluon, which are the components, right, which I find in my bag. So I sum, you see, each of the terms in this sum is incoherent. So I'm computing one, then I add it, I compute the other, I add it, and so on. They don't talk to each other, right? So this is the first non-trivial statement, very non-trivial. Actually, was Feynman, right, making this statement for the first time, saying this crazy idea, right, that particles inside the protons behave like free particles, right? So Feynman was the first to have this idea, right, that all our experience in everyday life was that the quarks are super tightly bound in the proton, so that even if we try to get one of them, we'll break everything, and we'll need a lot of energy to take one out. Okay, but in fact, Feynman said, well, at very high energy, they look really like a bag of proton. And this was the start of the parton model, which then right, evolved into what we call now QCD. But the logic really, right, if you go back to deep and elastic scattering, if you imagine that you have a photon with a very small wavelength that it can resolve the inside structure of the proton, what this formula says is that when a photon strikes one of the parton, this parton flies away without even noticing that he was going along on a train with his friends or her friends. Okay? So it's amazing, right? Because our perception of a proton is super tightly bound system. While this formula says that basically this interaction that we have between the partons are basically super small, that we can neglect them. So behind the parton model, there was this idea that very high energy, QCD, is free. It's an asymptotically free theory. So this was the idea that then inspired later the fact that QCD, the calculation of the beta function of QCD, was to found that the QCD was free and high energy, right? Everything turned up consistently, and SU3 looked the right theory for strong interaction. But it's all here, right? And this intuition, then the fact that very high energy, the quarks are basically free, is reflected in this formula that we are using here when we sum incoherently among all the fluxes of partons. Okay, so non-trivial, it looks trivial, it's not trivial at all. It took 20 years to figure this out, okay, or more. Okay, very good. First thing. The other very important point, which is again hidden here, is the fact that I'm really doing a convolution between the momenta of each species, okay, of each fraction of momentum for each I and J. And this convolution actually tells me that the probability of finding a parton inside the proton is factorized on the proton on the left, is factorized on the proton on the right, and above all, is factorized with respect to what we call the short distance coefficient. So once again, this relates to what Ian is explaining with the effective theory, right? This is an example of factorization between physics at different scales. So here, there is physics up. So imagine that this is your scale, this is mu f, this is energy, okay? So what we are really doing here, we are factorizing low energy low energy where low or high depends on this scale, which is arbitrary. So we set ourselves a scale, and then we say we put everything which happens below that scale in these two objects, which also factorize among themselves, which means that there is no interaction before the collision between the two beams. So it's a product of probabilities, not a joint probability function, right? And then I'm factorizing what happens at low scale here, and multiply by whatever happens in high scale and high Q squared here in the short distance coefficient. Okay? And then at 3 level, I have no problem. I can choose mu f as I want, basically, because there is no rule. But when I compute things at higher orders, I have to impose, right, that my cross section at the end will be independent of this scale mu f, which is 0. Okay? So the derivative of mu f, which is arbitrary, remember, when you do a factorization theorem, you introduce a scale which is arbitrary, you can change that, and the fact that your observable object does not depend on that scale gives you the renormalization group equation corresponding to this observable, and to the fact that somewhat these objects will have to be correlated somewhat in such a way that the mu f dependence will cancel among them, order by order in perturbation theory. Okay, so I'm summarizing something which we might discuss even further later. So this object at 3 level have a probabilistic interpretation, right? Because these are probabilities. When we go higher order, it's not true anymore because they can even be negative. Okay, there is no condition on the positivity of the f. The only thing you know need to be positive is sigma. And the other thing which is important is that at higher order, you really see that this separation is arbitrary because the objects that you do the separation with become scheme dependent. So they are non-physical. They depend on a scheme that you can choose whatever you want, right? The finite terms are not fixed. But the point is that once you have, for example, DIS, as I mentioned here, measurement. You make a measurement in DIS, you extract the F from DIS, and then you use them and then see in the same scheme, then your theory becomes predictive. That's the logic that we're using. So these objects are non-perturbative, but they evolve with the renormalization group equations, which in this case are called DGLAP, okay? Which are very well-known equation that tells you how the f evolve with the scale, okay? And once they are measured at a given scale, for example, in DIS, I can evolve them and use them in any other experiment. That's what we are doing. If we were really good, people are trying to do this, and this is one of the frontier, will be to calculate this object from first principle on the lattice, right? They are non-perturbative objects. They have a very well-defined quantum field theory definition, so they could be not easily, unfortunately, but they could be computed on the lattice, and then we would not need to do this game of measuring one side and using them on the other side. And then what about this last term? Well, this last term corresponds again, right, to the computation of basically this object here, right? But now the collision is between partons. I have a flux. The flux is the parton energy squared. And then I have to compute the matrix element and integrate over the phase space. So how does that work? Well, there, what we do for a collider is to do a perturbative expansion. So we rewrite this partonic cross section, and we expand them in terms of alpha s. So we look at the first term, the second term, the third term. So here is this way. I'll explain it. X plus, what did I write? Yeah, plus kappa. And here I have plus kappa plus j and so on, and plus L and so on. So in each order, so this is my leading order prediction, 3-level, if I'm able to produce it 3-level. Otherwise, I will go one loop. So for example, if I do Drell-Yan, the first term is like quark, anti-quark annihilation to a W, for example, here, and is 0th order in alpha S. Then and next to leading order in alpha S, right? So this is an expansion. This is alpha S to the 0 power in this process, alpha S to the first, alpha S to the second, and so on. And each term has a name. So this guy is called leading order. This one is called next to leading order. This one next to leading order, and so on. Okay? The order, the starting order is a characteristic of the process. So it's not always like Drell-Yan. Okay? Like TT bar starts at alpha S squared, and then I go on. Okay, so the starting order depends on the process, but then you put +1, +2 for the powers of alpha S. So what we learn is that if we are inclusive enough in the final state, that we are not sensitive to long wavelength radiation, then each of these terms is actually finite. Okay, so tomorrow we'll try to do a very fast and simple NNO computation just to give you the feeling how it works. But so just to give you now what it means, right? So for Drell-Yan, the next leading order will be to compute the one loop diagram. There are others, and then integrate over the phase space of one particle, and then to compute also the real corrections and integrate it on the phase space of two particles. And then if I sum these two contributions once they are integrated on phase space, my result is finite. And with finite, I mean IR finite. So it's not sensitive to long wavelength radiation, the radiation I was talking about before, the one with the minimal threshold in the detector. We will see how it works a bit more tomorrow. Today, we stay in the first term, but what I mean is that the beauty of this formula is that it's systematically improvable. It depends only on how strong we are in making higher order computation successively. And of course, if alpha, right, alpha, the scale of the W is roughly 0.1, right, it's 10%. So each of these terms, right, this will be a 10% correction, this will be a 1% correction, and then the law will be 1 per mil correction, and so on, roughly. Okay, so we can systematically improve it. Okay. Are there questions? Yes, please.
Can you maybe in the cross-section you wrote down, can you repeat what you said by the notation, the X and the NX and the X?
Oh yeah, thank you. So what I need, this will be nx prime, let's say. So thank you. I should have also corrected that. So this x is anything really that can actually anything you can think of. A Z, another Higgs, a top, a jet, a pion, everything that you can dream, right, is here, which can be written as a physical asymptotic state or not, right, depending on the level of your computation. But what I'm really doing here, this is when I sum over ij, I'm computing parton level cross-section. So these are, in general, partons, partonic objects. So gluons, like a top quark also, if I want, or a Z also. But in general, in the way we think it normally, the important part is that these guys are any parton. Okay, and that's the reason why here I put in parentheses plus k, because in next to leading order you might have only one extra partner, because otherwise you go, if you have two, you're here, but you might not have it because it's in the virtual. So the virtual has no extra partner, but it does not contribute here. It contributes here because it's higher order in alpha S, right? Because this has two powers of G, then I interfere it with the Born, and it keeps it to be alpha. This one, I interfere it with itself, I square it with itself, so it's also alpha. Okay? So that's the reason why these are the two different topology final state, but they enter, both of them, they enter here. And that's the reason why I always have to sum over all final state, because I need to combine them, to take them from different multiplicity and pack them together to get something which is infrared safe. Yes? Yeah. Yeah. Very good. Thank you very much. So this formula is not perfect, right, as everything in life. So in this case, the powers, right, that you are sensitive to in general scale with the power, let me be conservative here. So with powers of lambda, where lambda is lambda QCD as a scale, so lambda QCD is order of 200 MeV, right? So non-perturbative physics, long distance non-perturbative physics, might actually let them, the initial state talk, the initial state and final state talk, and so on. So it might break this naive way of factorizing it. Actually, this is a theorem, okay? So it's not like we are making this up. It's a very complicated theorem, right? Which tells you that there are always corrections which anyway scale, worst case scenario, they should scale like lambda over q. But if you have a very small momentum in your final state, you can have a correction which is also your momentum, transverse momentum in the final state over lambda. Okay, so this is good. So this is under control as soon as your q, so the hardness of your scattering, is significantly higher than lambda QCD. So if you have colored particle, right, which you want to detect and you want to predict a small pt, then this breaks. Okay, so the more exclusive you are, the more sensitive to this power correction you will be. So there is a full set of studies that study this kind of behavior, right? It's very important. And but normally in what we are doing, so in what I will doing today, when I look at the mass of the Higgs as a scale of the problem, this and the somewhat currently neglected, let's say, it's actually true that when you go n cube LO, which is the current accuracy for the Higgs, I mean, you reach a regime where you should worry about everything. Okay, but okay, let me simplify for the moment. Thank you very much for your question. Aaron, very good questions. Thank you. Yeah, you don't need that. If you want it, you can put it, and then you reintroduce this F. But if I only measure in the number of events where there is a Higgs, I don't, okay? So the less you ask, the easiest is your life. Again, right, like in normal days. Yeah, thank you. Thanks you. I, I when I said that I should promote X prime into X and X prime, I did it only one place, and it actually should be everywhere. So why? So now why this X prime? Even if I sum over all X prime, is not this one. Why? Yes, that's a good answer, but also because there is a, I mean, all this physics which happens here is encapsulated in an inclusive way into the F. Okay, but if I actually see, so imagine that mu F is 10 GeV or 100 GeV. So technically, everything which is lower in virtuality than 100 GeV is in the F. So if I do I produce a Higgs, and together with it, I run a jet clustering, and I see there is a jet, right, of 50 GeV. This event, where is it? Is here. I mean, is hidden. The probability of this event is represented by the F, not by this guy, because it's below the scale. So below the scale, all the physics is integrated out here, up to this scale. Is that clear? So it's always different X outside, because there is a lot of stuff which, even though we don't realize it, maybe, is really integrated up to mu F into the PDF. Okay. Okay, let me go on now. So let me now compute something. And the way we're going to compute it is really the textbook way, let's say. And along this computation, I hopefully, if we manage to do it until the end, otherwise we'll continue a bit tomorrow. We will learn a lot of details and basic also concept that will turn out to be very useful for us. Should I go on? Is it okay? Okay, so now let me specify and calculate the one of the most important cross-section at the LHC, if you want the cross-section. So if you go now to the LHC, sorry, I even had a very advanced animation here. Yeah, okay. So if I take, so I go to the CERN web page where all the calculations on the X are done. It's called X working group. And then I download the cross-section for producing a Higgs boson at the LHC. These are all, I mean, these are theory predictions. So they've been plotted as a function of the mass of the Higgs, because at the beginning we didn't know what was the mass of the Higgs. So we calculate them all, right, just to be sure. And then we plotted them. And then you see from this plot that there is one of them which is way higher than the others, which is this one here. So the red line is where the Higgs actually is, 125. And the cross-section, which I was mentioning yesterday, you read it out of here, is roughly 50 picobars. Okay? 50. So this 10 to the 2, 10, I'm right in the middle here. So it's roughly 50 picobars, which is what I told you about. So the second one is called weak boson fusion. I will mention it later, but it's already one order of magnitude smaller. Okay, so if you have to discover the Higgs, you focus on gluon, on pp2 Higgs. So that's the reason why we imagine now, we compute it inclusively, which means we add everything, but basically what we are saying, we are computing the first line, the blue line, a leading order, okay? Because the others are subleading. So if I include them with my f function or not, it changes my result by 10%. So I'm not that level of accuracy right now, okay? So I take my hope, right? And look at this plot which has been done by experts. So I'm confident if I compute the cross-section for the Higgs, I get something which is representative. So let me ignore the mu f now, because I'm leading order. So I'm not really sensitive to that. So let me let me just speculate for a second. What is the process where I can compute, I can produce a Higgs on its own with nothing else in my perturbative theory? Okay, so when I do the calculation perturbatively, I can imagine to have the Higgs and nothing else, and so on, and moving on, adding them partons one after the other. Okay, so I have two partons, which I don't know what they are, and then I have a Higgs. So what can I use as partons? Ideas? Okay. You are advanced. Thinking bar is a great idea. Thank you. What else? I'll come back to that in a moment. Hey, okay. You're spoiling my story. But okay, I'll take it. So you have gluons. So, I mean, can gluons be attached to a Higgs? So is this vertex present in the standard model? The answer immediately is no. Why? Okay. But even more than that, right? I mean, okay, so there is a number of reasons, okay? And so there are so many, I don't know, so many, no, but there are few. And so, but the most, there is one which in my mind at least is the most obvious one. So what was the answer? I mean, the X has no color, right? So it's not charged under gluons, under SU3, so it cannot couple to gluons. That's all, finished, over, right? And there is no vertex because it has no color at 3 level, right? At 3 level. So the Higgs cannot couple to because there's no charge, okay? And of course it cannot couple even to 2 photons, no? Because it has no electric charge either. The Higgs has the quantum numbers of the vacuum, and therefore has no charge, no any charge, well, of the, I mean, in the vacuum, right? I mean, there's an electroweak charge, but the electroweak symmetry is broken, so that's not valid. Okay, so this cannot happen. Okay, so what about this line up, anti-up X? If there is this one, there will be this one also. Is it okay? You should have them, actually all of them, right? U, D, C, S, V, and top, right? Which we wrote here, so I will not mention. Okay, so all of them are there. But what is the catch? The catch is that this coupling is proportional to the mass of the quark, right? Is the Yukawa coupling in the standard model. So in the standard model, the Yukawa coupling of a fermion is m fermion over v, prediction of the standard model, and therefore the coupling is proportional to the mass. Since basically all this coupling, all the masses here are small, actually this is not that small, we'll come back to that. So this might be a way, actually. Okay, so let me not say this, but otherwise we are bound to this one. Okay, now, so can we have this process as it is? Technically, yes. Okay, technically yes, because in the F, as I told you, depend on the scale. So they are objects which evolve with energy. So if I have my energy is high enough, I will also produce virtual pairs inside the proton. If my probe is higher enough in Q squared, I may see a TT bar within the proton. It's not forbidden by anything. Okay? So if I have enough higher scale, I might get this. The problem is that the scale we're probing now are order of the mass of the Higgs. And the mass of the Higgs is even lower than the mass of the top. So we could do that at super high energies. We could try to use this process as a bottler. In fact, there have been many studies on this. At the end of the day, it's not useful. Okay, so at the end of the day, really, what we mean with this process, naturally, are two things. Either I produce the top in the final state, which is what you would mean anyway with this process, that so what a gluon splits into a TT bar, then two of them, right? So you have two gluons, then they split in TT bar, they're very high Q square gluon, a TT bar here, and then two of them coalesce to do a Higgs. This will be the picture that we have in mind when we write this one. Then the other two top go collinear, right? And I don't see them. I have to integrate them out in the PDF. But this process, at the end, you see what it is, right? Is really T, X, and T bar, which at LHC we see, but it's a very small cross section. Is this one, you see? This one is hidden a bit. So it's a very much smaller cross section, and it's what we really mean when we actually say TT bar, when we say this one. Okay, so when we talk about this, we mean this in a regime where the spectator tops go very forward, and then I don't see them, and then they end up in F because they are below my mu F. Okay, so it's possible. You can do both ways, but this is super small, so I don't care right now. I'm really looking at the blue line. So all of these are all small. So we end up with your suggestion. Thank you. So the only thing we are left with now is the production of a Higgs through a loop. And as a recurring theme in these lectures, any reasonable person, right, who sees this the first time would say, "Are you crazy?" Right? I mean, you're telling me that you're going to build a multi-billion collider, right, to find the Higgs in this channel? I mean, through a quantum process, not even tree-level, not kind of classical tree-level thing. We have been given billions and billions based on this, right? Guess that this was the main process. Right? I mean, we are betting everything on of our knowledge of quantum field theory to find the Higgs, because to make this work, right, it means that I control quantum field theory at one loop. I mean, my data, I have already checked my data at the level of one loop with my theory, right? Which is actually the case, right? Because before there was lab, there was Tevatron, and we knew that the standard model was working and quantum field theory was working. Actually, we almost discovered the top that way at lab instead of producing it directly at Tevatron. Okay, so we're already confident that we managed our loops. Okay, but still, it's very interesting, right? That somewhat the main production mechanism at LHC is a quantum process. It's a process that classically would not happen. Right? So this certainly certainly something that you can tell in a cocktail party when you want to show off that you are a physicist, right? I don't know if it will work, but you can always try. Okay, so now what we need to do is actually to compute this amplitude. Okay, so and to put it in this formula. So there are a few technicalities here, which in the interest of science, I will now skip because are just the kinematics and how I reorganize the x1. Sorry, I'm really bad. The x1 and the x2. But what I'm doing now, I'm selecting one channel and I'm computing this cross section here. So let me try quickly to write how it works. So basically, what I need, right, is the partonic cross-section will be 1 over 2s, the matrix element square, the phase space for one object. In my leading order approximation, I had only one object in the final state. What is the phase space of one object? Is its 3 momentum divided 2 pi cube 2e of the x, the energy, or let me call it P0 if you want. Okay, and then I have conservation of momentum. I call P and Q, mu and nu, these two gluons. So remember, right, the phase space of M particle is the product of d3p I over 2 pi cube 2ei times 2 pi 4 delta 4 conservation of momentum. Okay, so the dimensions of a phase space are given by this formula. So for example, for n equal 1, right, which is this one, you have 3 minus 3 minus 1 minus 4. Okay, so it's minus 2. For n equal to 2, right, so you have 2 of this, 6, minus, minus 4, and this is, sorry, you have, so you have 3 minus 2 minus 4 times 2, the 3, so is 0. Okay? So the phase space of two particles is 0. I repeat, 2, this is 2 times 2 minus 4, because the delta is minus 4. So the phase space of two particles is 0, which will be useful later. It means that when I write the cross-section for a 2 to 2 scattering, right, the cross-section has dimension 1 over energy squared, right, is a length squared, 1 over energy squared. This is dimensionless, so the scattering amplitude for a 2 to 2 process has no dimensions. It's unidimensional. Okay, this will be useful later, but remember. So this is minus 2, have you said? So let me erase it. It's just a reminder for us. Okay, so I have to solve somewhat the phase space. So you see that there are I have 4 constraints, 3 conditions. So one condition is left, okay, and then you can show that this thing here is 2 pi the energy minus mx squared. Okay, you can do it. You introduce another delta that kills this one, and you divide by e, and that's the result. Okay, so the this phase space is actually a delta in the energy of the final state particle. You are telling me that the energy of the two incoming gluons have to add up exactly to the x mass, right? Because there is nothing else in the final state. So I have to select the gluons in that way. So my cross section becomes 1 over 2s m squared 2 pi delta of s minus m squared. Okay, then I define, as I did before, tau and y. So let me be, so I change variable. So d tau dy is the same as dx1 dx2. There is no Jacobian. And then I rewrite my formula in a suggestive way, because I can basically do one of the two integration, and the one which I'm doing is the is the integration of an energy which is fixed. Okay, so I repeat, there is a delta here. So I'm basically fixing the product of this to be the x. So I'm selecting one direction in the space of x1, x2. So I change variable, and what I'm fixing now is d tau. D tau has to be fixed to the x mass. Okay, so I'm only left with one integration, which is dy. Okay, so my final formula is sigma is equal to pi, the matrix element squared, mx s, the integral from log of tau to minor log of square root of tau 0. Tau 0 is x1, x2 mass of the square. And then I get dy g, if you want. So let me write it in the right way. And g, right, tau e plus y. Okay, so this thing here as a name is called Parton luminosity. It does not depend on the final state. It's an object which is built up out only as a convolution of PDF because the physics is clear, right? I mean, you fix the energy of the product of x1, x2, then you have many ways, right? You can integrate over the fraction of relative momentum that you form, you get to get a given energy, right? You can integrate on x1 and x2 with a constraint that they give a fixed energy. And then you are only left with the integration of the rapidity of center of mass. Okay. So this is the Parton luminosity, or vice versa, right? So you integrate on the rapidity and you get something which depends on tau. Now, tau here is fixed by the mass of the x, so there is no integration over tau in our case, because there is a delta that comes from here. Okay? So normally you would integrate over tau, but in our case, there is no tau integration because it's 2 to 1, not 2 to 2. Okay? So that's the kinematics. I'm not very, okay, so that's a detail, but just to get you the formula. So now what we need really to do is this computation, which is the fun one. Okay? So this was all warming up. Now we do the real work. Ready? You want to stretch? So we compute the loop. So we prepare 3 blackboards. And voila. Are there questions? Okay. So we compute the loop and we write the amplitude. Okay. I am equal. First of all, we learn in quantum field theory that the fermion loop gives a -1. So let's put it there so I don't forget later. Then I have 2 couplings from QCD, right, which is GS, G strong. Then let me finish also QCD. Then this is a loop, a fermion loop. There are 2 color matrices here, TA and TB. So this is trace of TA and TB. TA and TB are the generators of SU3. TA, TB equal FABC, TC for SU3. Okay? So I assume that you have seen them, hopefully. Then there is the Yukawa coupling, minus I m of the quark divided by V. Okay, so I'm putting all the elements that I care. And then finally, and so what unfortunately for us, but also fortunately because it's really fun, is really that I have to do the integral over the loop momentum. So the loop momentum I call L here, and I go this way, aligned with the arrow. So before I go on, do you have any comment on so this is the diagram that I need. Is that all? Because you know that when you deal with Feynman diagrams, you have always to check first if you draw all of them, right? Did I draw all of them? Is there one diagram? There are two diagrams, right? And because I can run this guy on the other way, and since the two gluons, are different, right? Because one is coming from here, one is coming from there. So this is another diagram. So I have two diagrams actually. So I either draw them like this with the same arrow and exchange the two gluons, or I invert the arrow. You draw it as you like, but there are two diagrams. Okay. And then, as I said, we have a loop. Now, this loop is four-dimensional loop, no? But what? But I have to be careful now, because when I compute loops, I learn it the hard way. I get divergences, ultraviolet divergences, infrared divergences. I get all kinds of divergences, which I learn how to regulate with dimensional regularization, right? So now, so I would say, well, let me conservative, and let's put D here. And someone who pays attention among you will say, but why you worry? Why do you worry? So why I worry about this? Should I worry or should not worry? So let's take a poll. Should I worry? Okay. So should I worry about ultraviolet divergences or should I not worry? Who says it's better always to worry? Who says life is short, better not to worry all the time? Okay, you see that there are no clear cut answer. This is one example, which is a lesson that this time, even though you should not worry, you better worry. Okay? Right? Why? So, why? Normally, I would have told you no problem. There is no ultraviolet divergence. Why? Because I told you, right, that there is no vertex in the standard model like this one, right? So the standard model is renormalizable. So if I get an ultraviolet divergence here, where do I put it? Right? Which coupling do I absorb to in the divergence? I know, I learned in school, it's written everywhere that the standard model is renormalizable. So it's impossible in the standard model to get a divergence in this diagram. This argument is correct? Yeah. For the standard model, in fact, not for the standard model. So this is a difference which is important with respect to effective field theory, in fact. But if you have a renormalizable theory and you calculate the first time a loop of something which was not present at tree level, it's finite. I mean, you know by the argument of renormalization. You don't have to worry. You know beforehand it's finite. This is not true in effective field theory. So be careful, because if you do your computation next to living order, you're going to go through it one day or the other. And you will find that it was something which was not at tree level, but it's still divergent. And the reason is that there is mixing with other operators, and therefore it's not guaranteed that it's finite. But here, all operators are dimension maximum 4, so there is no mixing. So then you all you all happy, right? And then say, okay, now we put 4 because it's finite. Well, it turns out that if you put 4, you get the wrong result. Okay, which is a lesson. It's a very interesting lesson, which I will show you where you would get it wrong. Okay, so this tells you that dimensional regularization is actually useful and necessary. This was there was a long debate even in the literature. People wrote papers on this saying that no, it should be, there was a debate, but at the end, the story is that you have to keep it in D dimension, and then when at the end you find that everything is finite, then you're sure the finite term is correct. So it's a bit, for those who ever calculated an anomaly, so who has calculated an anomaly in their life so far, like in the standard model, you remember, right, there is a very subtle thing happening in anomaly calculation, right, apart from the gamma 5 properties, but there is really an epsilon term that cancels a 1 over epsilon term, and you get a finite term, remember? So you will see that this is happening here too, actually. Nothing to do with anomaly, but it happens. Okay, so then you have a numerator, which we will comment on, and then a series of denominators. And then we have the i's of the propagators. And then we have the polarization vectors for P and Q. They are in the initial state, so they are epsilons, not epsilon stars. Okay, so how much time do we have more? Let me stop. 20 minutes most, okay. So will be a record calculation. So, less, 15? 15, okay. Okay. Okay, so now, what is, so we have a numerator and the denominator. What is in the denominator? The propagators of the loop, okay? So let me write them. So there are 3, and the 3, are L squared minus MQ squared, L plus P squared minus MQ squared, and L minus Q squared minus MQ squared. Okay? There are 3 because there are 3 fermions, right? And I'm putting the gamma on the top, so they're squared. Okay, the propagator. So in the numerator, I will have P slash and so on. So so the numerator, which I write here, is the trace of L plus MQ gamma mu L plus P plus MQ 1 L minus Q plus MQ gamma nu. Okay, so if you have done it, it's very easy actually to write it. It's a bit more difficult to calculate, but to write is easy. You put the propagators and the numerator is a trace because it's a closed loop of fermion. Okay, now what do we do with the denominator? It's in the notes, but in the end we use a Feynman parametrization. Who has seen a Feynman parametrization before? Fantastic. Great, so you are a dream class. And therefore, the denominator, you combine them all. Okay, you combine them in one denominator. And so let me do it 2 things in one go. And what I do, I combine them and then I make a shift in the momentum. Why? I make this shift to make the denominator a quadratic function in L. Remember? Because when I write it, the denominator has a linear term in L. This is not good because then I have to use a spherical symmetry. So I make a linear shift and I reabsorb the linear term, and I get something which is quadratic in L prime. It's all in the notes. I don't care too much about this right now. What I care though is what happens in this trace. Okay, so look at this trace here. So it looks a bit like the trace that I would have calculated if here I had another gluon or a photon, right? And remember, if I have 3 photons in a fermion loop, it cancels, right? These 2 diagrams will cancel by Fourier theorem because of C. But if one is a scalar, these 2 actually have the same sign, so you get factor of 2. They don't cancel. Okay, so I have to remember to put a factor of 2 at the end because these 2 are equal diagram. And you can see it from here. You just change the position of 1 and then you get the same thing. But now you look at this and you see there is a number. So if you take, for example, this term, there is 1, 2, 3, 4, 5 gamma. 5 gamma is not a good number of gammas in a trace, right? Because it's 0. The trace of an odd number of gammas is 0. So I only can get an even number of gamma that will contribute to the non-zero term. But to get an even number of gamma, I have to sacrifice one of the slashes, okay? Which means that I have to pick up by force one of the masses. Okay, is that clear? Because I only need, I only have, I end up only with an even number of matrices. So my trace is actually proportional. So I do the trace then, is a series of tensors. So these are primes. No, sorry, these are not prime yet. I still have to do I have not done this yet in the numerator. I'm doing it later, okay? So I get this form here. So it's a tensor. And you see that the really thing that I'm interested in is this term here. The old trace is proportional to the mass of the fermion which is running in the loop. This mass is not this mass. Not because I made a mistake and I call it small q, right? But because this is the kinetic mass in the loop. This one is the Yukawa coupling, which I rewritten in terms of the mass. Now, in the standard model, it's the same, right? Because the Yukawa coupling is the same as the mass term. But they are 2 different objects. This is a coupling. This is a real mass running in the loop. In the standard model, they happen to be the same thing. But for example, in SUSY, they're not. Right? If you take 2x doublet model, right, the coupling of the top will have a cotangent beta in front, right? So they don't need to be the same. In the EFT, they are not the same, and so on. Okay. So now what I need to do, there is one more step, and this brings me to the point which I was telling. You see that I have an integration to do. I have the modification of L, and so the change in L prime. But then I also have this tensor here to calculate over this object. Okay, so I have to do a computation which is this. So let me use kappa as a generic momentum. This is 1 over d g mu, the integral in d dimension. Right? So it's a symmetric tensor. This is a spherical integral, 2 symmetric tensor. The outcome is an invariant, which is g mu nu, times dimensionally a kappa square. However, in d dimension, there is 1 over d in front, right? In 4 dimension will be 1 over 4, but in d dimension is 1 over d. So once I do the integral, and I shift also the momenta, I get this expression dl prime, the two Feynman parameter, and then I get g mu nu, which multiplies mq plus l prime 4 minus d over d plus mx squared xy minus 1 half plus p nu q mu 1 minus 4xy times the propagator combined. Propagators combined. Again, all details are in the write up if you want. And now you see something interesting, because you see there is this term here which multiplies 4 minus d, and is a term which scales like L prime squared. But L prime squared divided by L squared to the third power is L to the fourth, which is divergent. So this integral here is divergent in front. So in dimension, it will give me 1 over epsilon, the integral. This term, 4 minus d, is epsilon. So 1 over epsilon times epsilon, it will give me a finite term. That finite term is important. It's not, if you don't include it, you get the wrong result. Okay? So now you have two scalar integrals, this one and the one with no L. They are in the notes. Let me give you the final result, so at least I stop in a in a clean way. The only thing I care now that you remember is that this thing here is finite and is epsilon times 1 over epsilon, like when you do an anomaly. Okay, it's a remnant. So the result, which we will comment further at this point tomorrow, but let me write it. So the m for g to x is minus alpha s. Now I'm putting the g's squared into alpha s. mq squared delta ab, color, right? Color, the trace of TA TB is delta AB divided by 2. And then I have a Lorentz structure which is obvious, right? I mean, this tells you that we didn't screw up anything trivial in the computation, because this structure is dictated by what? This I could have written from the beginning. Yes, but more, even more fundamental. No, maybe not fundamental, but more inspiring. Eh? I didn't hear what you said, but it's too long. No, it's easier. It's easier. Yeah, symmetry, but which one? Lorentz and gauge, right? It's gauge symmetry. This one, right, is a tensor in two indices. This is like an abelian. There is no non-abelian structure. So it means that if you contract with the longitudinal polarization, it has to be 0, independently of all other polarization. And the only way that is 0 is this one. The only structure is like the, when you calculate the polarization of the vacuum in QED, you get this structure also, which is dictated by gauge invariance. So this is gauge invariance alone, and then you get a very simple answer combining all terms, right? So you get this integral as a result. Okay, so let me just give me 2 minutes that I comment, and then we will do all the fun stuff tomorrow morning at 8 and 9. Okay, so what do I see? Well, first, let me comment on the masses. So let me call this MQ and MQ, right? So I leave the coupling out, just for us the way to think. This M is the M that was coming from the trace. Now, if I look at this integral, right, here, I can take this MQ out here, and put it here, right? And then, if I don't make any color difference, I cancel it. So and only remains inside here, right? So the only dependence on MQ of this diagram is inside this function, which I call I of mx over mq squared. Outside this function, this one, which is a function of this ratio, there is no mass dependence because that's cancelled. Okay, and then the other thing that you see is that if mq goes to infinity, this EI is equal to 1/3. That means you have to calculate, but it's equal to 1/3. Okay, so this term goes away, you do this integral, you get 1/3, a number. So you find something which is super weird, no? And somewhat unexpected. If you think in terms of effective field theory, something very fishy is going on. Because I have a particle which is heavy. If I take this particle heavy, I know from the decoupling theorem that my result should scale with that variable and should get to 0, right? Not to a finite number. It should just disappear and scale it down to 1 over mq, which is not the case here. And it's not the case for a number of coincidence, quote unquote, because of this mq which was coming out from the trace, because the coupling is exactly mq, right? And then it all boils down to canceling this. So it looks like a conspiracy, okay? And in fact, it is somewhat a conspiracy. And as all conspiracies, it's good to think about them. So we'll talk about conspiracy tomorrow morning. Thank you.